Welcome back, ladies and gentlemen. Before I begin today, just want to mention that it is an absolutely gorgeous day outside today. But what am I doing instead of enjoying this beautiful autumn weather that we have this week? I'm here talking about solutions. And I'm not just talking about the answer to a problem. Yes, there will be problems in this unit, but we are focusing on solutions, homogeneous mixtures, and how we can calculate concentrations of those. How do we determine what are the individual components of a solution? It's going to be an exciting set of time for us today. So that being said, let's go ahead and get on to the student learning objectives. So we got a lot of things that we're going to take care of in this particular unit as we approach the end of this course. We have a couple of chapters left to go, but after that we will be done, we will be finished, and we will move on with all of our lives. So pretty exciting to approach the end of a semester, as you all know. So what are our learning objectives for today? Well, hopefully you'll be able to know the defining characteristics of a solution, define solute, solvent, know some factors that impact solubility, use terms like saturated, unsaturated, supersaturated, dilute, concentrated, aqueous, non-aqueous, describe the solution process at a particle level, be familiar with factors that increase or affect the rate of a solution formation. You should be able to utilize the solubility rules, calculate percent concentration by units mass volume and mass volume percent. Use those as conversion factors, determine types of substances that would be a strong, weak, or non-electrolyte, and use molarity as a conversion factor, and calculate new concentrations by using a dilution. So we got a lot of things we're going to take a look at today, but I'm really excited to get going, so let's just dive on in. And I think the very first thing we probably ought to do is define the term solution. Solution is just simply a homogeneous mixture of two or more substances, with each substance retaining its own chemical identity. So remember that homogeneous mixtures are uniform throughout. That is, you cannot discern the individual components that make up a solution. And as we mentioned before, they retain their own chemical identity. So this is not a chemical change process, but rather a physical change. So I'll use salt water as an example. When you take salt and you mix it with water, the salt dissolves and you can no longer see it. However, if you were to evaporate or boil off the water, you would get the salt back out of it. So that is indication that the chemicals have not reacted in a way where they no longer retain their chemical identity. So again, when we're looking at homogeneous solutions, we're looking at mixtures that retain their own chemical identity. I can get the chemicals back out of it through physical means, such as boiling or evaporation, rather than chemical means, such as a chemical change per se. Now, we refer to the different components of solutions by different names. The solute is the component of the solution that is of lesser amount. Quite often, this is going to be a solid. So I'll go back to the salt water example. We take our salt, that's going to be our solute. Typically, it's a lesser amount. And then our solvent is the component that is of the greater amount, and most often this is going to be water. In some instances, depending upon the polarity of the substance you're trying to dissolve, it could be something like hexane or octane, again, depending upon what you're trying to mix together. So if we think about sugar water, sugar would be considered the solute because it's of lesser amount. Again, that is also the solid. And then the water is going to be the solvent, which is that is in the greater amount. Most often, like I said, the solvent will be water. And then Powerade is a homogeneous mixture of a variety of different chemicals. However, the solutes in and of itself would be things like sugar, high fructose corn syrup, a little food coloring. If you look at the back of a label of a Powerade, you have a variety of different ionic compounds in it, which is where the term electrolyte comes from. And then the solvent itself is going to be the water that you're dissolving it in. So pretty straightforward. Just need to look at the ingredients list and just think a little bit about what is the individual components, or what are the individual components of the solution in and of itself. So let's consider some of the properties of homogeneous mixtures. The first and foremost, they're going to contain two or more components. Again, it is a homogeneous mixture. They're of variable composition. So what that means is that I can add a lot of solute or very little solute. So the composition is going to vary depending upon how much solute I end up adding. If we add a lot of solute, we would refer to that as a concentrated solution, whereas if I add very little solute, I would call that a dilute solution. Properties change when solute-solvent ratio is changed in and of itself. So if I take a look at the solution on the right-hand side here, if I had to guess, this is maybe like a solution of like iron nitrate or something that produces kind of that orangish color. But if I added just a spoonful of the iron nitrate, as you see up above, I get a fairly dark orange solution. If I only added half of a spoonful, then I would end up with a solution that is not quite as orange because I have less solute that is dissolved in the solution. Furthermore, if I add 2 scoops of the iron nitrate as opposed to just 1, then I'm going to end up with a darker solution. And the amount of solute in the solution can change some other properties other than just the color. You're talking about something maybe like electrical conductivity. As we mentioned, ionic compounds, if they dissociate, if they're soluble, they will conduct electricity in solution. Dissolved solutes are individual particles, so what that means is that if I have a compound, most often it is going to dissociate or dissolve into other smaller compounds or elements. Again, that depends on the solute that you're trying to dissolve. And this remains uniform throughout. Notice that it never really settles. So the orange solution, all of it's going to stay orange. It's never going to completely separate out. That's part of the definition of a homogeneous mixture. And the solute can be separated usually through the process of evaporation or boiling. So if I heat the solution, I can get the solute and solvent to separate through the process of physical means, such as evaporation or boiling. So these are just some characteristics of what you might find as a solution. I also want you to keep in mind that solutions do not necessarily just come in liquid form. You can combine a variety of different states of matter to get a variety of different solutions, and these solutions have different names. So for example, if I were to take gas and combine it with a liquid, I get something that is called foam. Liquids and liquids form emulsions, liquids and solids, gels, and so on as you kind of work your way down here. But I just want you to understand that solutions are not just liquids in solution. There are far more different ways that we can mix and create homogeneous mixtures rather than just having a solid dissolved into a liquid. So there are several other things that we want to consider when we're describing the characteristics of solutions, one of which is what is known as solubility. Solubility is simply the maximum amount of solute that will dissolve given an amount of solvent under certain conditions. Once the saturation point has been reached, no more solute will dissolve. So I want you to think back to your childhood, or maybe back to my childhood. As a common beverage, we used to drink Kool-Aid, and in order to make Kool-Aid, you had to mix sugar with a flavor packet and then dissolve that into water. Now, depending upon how much sugar you add, the sweeter the substance would become. But there is a point where no matter how much sugar you add, it will not dissolve. Or there will be some amount of it that will dissolve, but not all of it will dissolve. So if I take a look at the example on the right-hand side here, I have pure water and I keep adding a little bit of sugar each time. Well, eventually, there's a point in which the solution can no longer dissolve any more sugar. So if I keep adding more sugar, it just forms solid at the very bottom of the solution. This is when a solution is saturated, as we would say. That is, it's reached the maximum amount of solute that will dissolve given an amount of solvent. So I can either do one of two things to get rid of the excess sugar. I can either remove the solid sugar out of the bottom, or I can add more solvent, and that will dissolve the rest of the sugar solution. Now, there are several factors that play a role in solubility. So a good example would be that most solids become more soluble with increasing temperature. One way we would get more sugar to dissolve in our Kool-Aid is we would actually use warm water instead of room temperature or cold water. Warm water allows for more sugar to dissolve in the solution at that given time, and typically when you cool it back down, it will stay in solution, so it won't precipitate out as a solid. So increasing temperatures often result in an increased amount of solubility. Gases become less soluble at higher temperatures. Think like a carbonated drink. If you try to dissolve, or you notice that you've got a Coke and you open it up, first off, the Coca-Cola is under pressure, but as you open it up, you start to see the gas bubbles escape. Well, if you were to warm that soda up even further, the gas bubbles are going to escape at a larger rate. So pressure, in all honesty, has little impact on the solubility for solids or liquids, but increases the solubility in a liquid as the pressure of a gas increases, which is, again, why carbonated beverages are under pressure. That high amount of pressure allows for the carbon dioxide bubbles to dissolve in the water or in the soda, resulting in a bubbly, fizzy drink. But as soon as you release that pressure, the bubbles start to come out of the solution. So just a couple of notes on ways and factors that solubility can be increased or decreased. So let's talk about a couple of more vocabulary terms that are related to the idea of solubility. The first is what is known as a saturated solution. A saturated solution is one that contains the maximum amount of solute that can be dissolved under certain conditions. An unsaturated solution would be a solution that contains less than the maximum. And a supersaturated solution would be one where the solution has gone beyond the maximum amount of solute that can be dissolved. That's under certain conditions. So the example here is adding in, I'm not really sure exactly what chemical we're adding in here, but 5 grams into 95 grams of water, it is dissolving. So that tells me that it is unsaturated. If I add in 9 grams, apparently 9 grams is the most that can be dissolved in 100 grams of the solution. So 9 grams is the max. Once I reach 9 grams, then the solution is considered saturated. If I add in more than 9 grams, that would result in the solution would still be saturated. However, we would end up with a solid that appears at the very bottom of it. A supersaturated solution would be where we have some certain conditions where we heat it up and then we cool it back down, and you could get the unsaturated amount of the solution. You could get some of the precipitate back out of it. So I want you to imagine a hypothetical scenario where we're dissolving sodium chloride in water. The maximum amount of sodium chloride that can be dissolved is 40 grams in 100 grams of water. So if I dissolve 25 grams, 30 grams, 31 grams, etc., it's an unsaturated solution because I can still add more to get to the saturation point. The saturation point is 40 grams. Once I've reached 40 grams, my solution's saturated. If I attempt to dissolve more than 40 grams, the solution is still saturated. 40 grams will dissolve, but whatever is left over will be at the bottom of the beaker. So I want you to make sure you think mathematically about that. We're really not going to dive into supersaturated solutions, so I wouldn't be too concerned about utilizing that term. But just focus on the saturated and unsaturated. I can dissolve salt up until I get to that 40 gram point. That would be considered an unsaturated solution. Once I go beyond the 40 grams, my solution is saturated. However, I'm going to have some solid that is left over at the very bottom of said beaker. Now, there are other terms that we use to describe solutions, one of which is concentrated, and concentrated solutions are going to have a high amount of solute compared to what can dissolve. So you can see solution on the left here, we've dissolved the same amount of solute, but we've limited the amount of solvent. So the ratio of solute to solvent is quite high, which is why it appears to be a darker color blue. Dilute solutions have a low amount of solute compared to what can dissolve, and that's what you see here on the right-hand side. Aqueous solutions are those that are dissolved in water, which is where the term aqua comes into play here, it means water. And non-aqueous solutions are dissolved in something other than water. So sometimes hexane, again, it just depends on the polarity of the substance you are looking at. So when solutions form, they form through the breaking of solute-solute bonds. So imagine you're taking a solid piece of NaCl and you're putting it into water. Well, 3 things are going to happen here in order to make a solution. The first is that the solute-solute bonds are going to break. That is, the lattice structure that is in the ionic solid is going to break apart and you are going to get individual ions. We need to break apart the solvent-solvent bonds, and what's holding the water molecules together in the solvent is hydrogen bonding, so those need to break. And then the solute-solvent bonds, that is, the bonds that are going to form between the solute and the solvent, are going to form. And the ions become hydrated, they become surrounded by water. But what I want you to notice on the right-hand side here is the orientation of the water molecules that are surrounding the individual ions. If we remember back from our polarity unit and our intermolecular force unit, you know that opposite charges attract one another due to Coulomb's law. So notice around the positively charged ion, the oxygen part of the water molecule is facing inward, and that is due to the fact that that positively charged ion attracts the relative negative charge on the oxygen in the water molecule. In addition to that, the negative charge down at the very bottom right here, the hydrogens are attracted to it because the negative charge of that ion attracts the partial positive charges on the hydrogens. So again, the orientation of the water molecule is very important here for hydration to occur. And again, this is due to Coulomb's law. So this is what happens when ionic compounds dissolve in water, is that they dissociate into their ions and then the water molecules completely surround them. So what are some factors that impact the rate at which a solution forms or which something dissolves when we form a solution? The first is surface area. Think about crushed ice versus cubed ice. Cubed ice will make your drink not as cold as quickly, but the ice cubes will last longer because they don't dissolve as quickly because they have a relatively low surface area. There's very little coming in contact with the ice cube. Crushed ice, however, will cool your drink down much faster due to the increased surface area. However, the ice will dissolve much more quickly. It's the same concept when you're trying to take a solid chunk of something and dissolve it versus taking something that's been crushed up into a powder and dissolving something. The powder will dissolve much faster. because the surface area of that solid is much greater. Agitation. Stirring disperses particles more rapidly, increases the amount of energy that's in the solution, and thus we dissolve it more quickly. It's like taking sugar and putting it into water and letting it sit versus stirring it up. When you stir it up, it disperses the particles more rapidly. It results in more collisions of molecules. We'll talk about collision theory when we get into our kinetics unit. But the more collisions you have of molecules, the more likely you are to dissolve and increasing the rate of solution formation. And then lastly, temperature. Higher temperatures result in more frequent collisions, resulting in a higher rate of formation of a solution. So it's like dissolving sugar in cold water versus dissolving sugar in hot water. Hot water has a higher rate of molecular movement. We talked about that when we talked about kinetic molecular theory. The higher the movement of those molecules, the more collisions you have, and the more collisions you have, the faster the solution is going to form, or the quicker it's going to dissolve. So there's lots of factors that play a role in how quickly a solution is formed. There are some generalized rules, however, that determine the solubility of a compound in and of itself. Some substances do not naturally dissolve in one another, such as oil and water, which is what you see on the right-hand side. Well, what's the reason behind that? Well, we use a generalized term that's called like dissolves like, and basically this means that polar substances will dissolve in substances that are polar, and nonpolar substances will dissolve in nonpolar substances. So in this instance, water, as we all know, is polar, and oil is a nonpolar substance. So as a result, the two do not mix. Ionic substances in water is a bit more complex. We have to use a chart in order to figure that out. There's not really a set of simple rules that govern whether an ionic substance will dissolve or not. So we use a solubility chart in order to figure that out. And you see that here on this page. So here you can see that there are some soluble compounds, some insoluble compounds, and exceptions to these rules. Remember, exceptions to the rules will be the opposite. So for example, if I take a look at this chart and I look at soluble compounds that are in group 1A, that contain the ammonium polyatomic ion, the acetate polyatomic ion, or the nitrate polyatomic ion. These will always be soluble. Soluble meaning that they will always dissolve in water. There are no exceptions to that. Chloride, bromine, and iodine, and sulfate, most of them will dissolve in water, but have some important exceptions. So for example, silver chloride, silver bromide, lead chloride, lead bromide, mercury chloride, mercury bromide, those will not dissolve in water and would be considered insoluble. And then the reverse is true if I look at the very bottom of the chart. At the very bottom of the chart, we have a list of insoluble compounds, but some exceptions on when they are soluble. So make sure you understand and know how to use the solubility chart in order to determine whether something will or will not dissolve in water. So just a couple of practice problems for you here. Think about what we've talked about in terms of polar and nonpolar substances. Think about what we've talked about in terms of the solubility chart that is on the right-hand side. Take a couple moments, predict the solubility, whether they'll be soluble or insoluble, and I'll meet with you back here in just a moment. All right, so as we take a look at some of these compounds, we need to think about polarity, we need to think about using that solubility chart. So the very first problem that's here, it says methane. Oops, I'm using the wrong color here. It talks about methane, a nonpolar substance in water. Well, if you remember what we talked about previously, water here is polar. And so attempting to dissolve something that is nonpolar in a polar substance will be insoluble. The two will not mix. So this is going to be insoluble for the first one there. Next one is AgCl in water. So if I go and look at the chart, I'm going to look for chloride. And it says that chlorides are soluble. However, silver is an exception to that. So this is actually going to be insoluble. Same reason, it is an exception to the solubility rule that you see up at the very top here. Next one's NaOH. Look at it a couple different ways. NAs are always soluble. OHs are insoluble except for group 1 ions, so Na is included in that, so this is a soluble compound. And lastly, K2SO4. I'm given my sulfates here. They're soluble. We have a couple exceptions here, but potassium is not one of them. And then potassium always soluble as well. So these are soluble, meaning that it will dissolve in water. So one thing to make note about the solubility chart is that you will not find things that are contradictory. That is, in the top part of the chart, it won't say that it's soluble, while in the bottom part it says that it's insoluble. The rules will always correlate with each other. So you're never going to have one where it says one part of it's soluble, the other part's insoluble. If you do find that, go back and really look at the rules closely and make sure you're looking at the right things, because that will be how you determine whether something's soluble or insoluble. All right, let's keep moving along here. So most of the rest of this unit is going to be focusing on calculating concentrations of solutions. And concentration just refers to the amount of solute present in a specific amount of solution. The higher concentration something has, the more solute per unit of solution. There's a variety of different ways that we go through and calculate this. The book in this class is more geared towards the medical concept of concentration versus the chemistry concept of concentration. It doesn't mean that we can't use both when we go through and discuss this, so we will be using both. So the first couple ones are going to be more along the lines of the medical usage of concentration. And so the first one here is percent by mass. The second one is percent by volume. And then the third is mass volume percent. So there's a couple of different ways to go through and do this. I'm going to stick with what the book shows, but I do have other videos on this channel that do go through and talk about how to go through and calculate them a little bit different way. So if you just type into YouTube mass percent or search my channel for it, you'll be able to find plenty of videos that showcase how to go through and calculate this in a variety of different ways. So that being said, let's see what we got. So the first question here is percent by mass. And so it's anytime you take the percentage of something, it's always a good rule of thumb as well, is that if you take the percentage of something, it is always the part over the whole. So in this case, we're going to be taking the mass of the solute, that is the smaller component of the solution, and we're going to divide that by the entire mass of the solution in and of itself. Remember that the mass of a solution, remember that solution is solute plus solvent. So that actually gives us a couple of different conversion factors we can utilize with this. I want you to keep in mind that second bolded statement. It's one of the most important statements you're going to find in here, is that solution is solute plus solvent. So what that means is a couple of different things. The first thing it means is that a 10% by mass solution would contain 10 grams of solute per 100 grams of solution. And that makes sense, right? Because 10 divided by 100 is going to give you roughly 10%. However, a 10% mass by solution would also give you 10 grams of solute per 90 grams of solvent, right? Because solute plus solvent equals solution. So 10 plus 90 equals 100. So there are a couple of different conversion factors that we can utilize as we go through and do calculations with this. We can say that there's 10 grams of solute per 100 grams of solution, but we can also say that there's 10 grams of solute per 90 grams of solvent. So both of these are going to be used as conversion factors as we go through and attempt to figure out some different ways of calculating components of a solution. So you'll see that as we continue to work through some of the practice problems we're going to experience here in just a couple moments. So the first question here says, what is the percent by mass of 9.3 grams of sucrose in 97.8 grams of water? So the key thing to keep in mind here is the formula that we're going to be utilizing. It is the mass percent formula, which is listed here on the right. And the mass percent formula specifically states it is the mass of solute divided by the mass of the solution. So as we evaluate this, we're going to evaluate it the same way we've been doing every single problem in this class. We need to identify what is given to us in the problem and then utilize the information in the problem to come up with a roadmap in order to be able to solve it. So if I look here, we're given the mass of the solute and the mass of the solvent, and what's unknown is the percent by mass. Well, what I need is the mass of the solution, but remember that solute plus solvent will give you the mass of the solution. So what I'm going to do here is I'm going to take 9.3 grams, which is the mass of the solute, and then I'm going to divide that by the sum of 9.3 plus 97.8. I'm then going to multiply that value by 100 and get 8.7%. Now, often percent by mass is given as percentage, and then it will say M over M to indicate that it is mass over mass. Volume over volume will be V over V, and mass over volume will be M over V. So just keep that in mind. And also quite often afterwards, and I didn't indicate that here, so I apologize, but the word sucrose would be in it as well to indicate that it is an 8.7% solution of sucrose that is dissolved in water. So just keep those things in mind as we continue to work through some more practice problems. Secondly, we have percent by volume, and this is volume of solute divided by volume of solution times 100. The only difference here, though, is that the volumes are not additive, and part of that has to do with the polarities of the substances and the different densities that they have. So different volumes are not necessarily going to add up to equal a total volume. So you see here you've got 250 milliliter samples of solutions. Well, when you add them together, you do not get 100 milliliters. And that seems a bit odd. But again, it has to do with factors such as polarity and density, things you don't have to really stress out about. So very similar to the equation before, it is volume. And so we are going to do solute over solution, part over the whole, and then multiply by 100 to get our final solution. So let's take a look. The next question asks us to determine the percentage of ethyl alcohol in a strong mouthwash. This brand has 27 milliliters of alcohol per 125 milliliter sample. So in this particular instance, our volume of solute and our volume of solution. So we really don't need to do anything with this other than really just plug in and solve. And that's the difference with volumes, is there really aren't going to be any quote-unquote trick questions where I would ask you to calculate the solution based off of the solute and solvent. You're given solute, you're given solution, go through and calculate it. And that's why it's so important. As you do these types of problems, it's so important that you label everything appropriately, particularly solute, solvent, and solution. So that way you know if you need to add or not based off of the information in the problem. Regardless though, here, we have our information. We're simply just going to plug in and solve. So we're going to take 27 milliliters. We're going to divide it by 125, multiply by 100, round to 2 sig figs. We end up with 22% by volume of alcohol in mouthwash. Pretty straightforward there, all right? Let's keep rocking and rolling. So the last percent composition style of problem that we have here is the mass volume percent. And it is the mass of the solute and the volume of the solution. So same thing. Volumes are not additive like masses. So we're going to treat this the exact same way we did the very last style of problem, where we're just going to get the mass, get the volume, and divide the two. I may ask you for a couple of other parts of the problem, but you would have to go through and do some things algebraically in order to solve for that. But to just break this down here, let's say we hypothetically had a solution that was 2.3%. Well, that indicates that there's 2.3 grams of solute in 100 milliliters of solution. And again, we can use that as a conversion factor moving forward. So here we have another question where a solution is prepared by dissolving 20 grams of sucrose into enough water to make 350 milliliters of solution. Determine the mass volume percent of glucose in the solution. So again, we identify what we're given and what we're solving for as we work through these style of problems. So you have a mass of solute, you have a volume of solution. We just need to simply take those two values, divide, and we can solve, right? So 20 grams over 315 times 100 results in a 6.35% mass by volume of sucrose in solution. So these problems are relatively easy to go through and figure out, but we can make these a little more complicated and a little more complex based off of the information that's given to us in the problem. Let's see what we got moving forward. So each of the percentages solved can be used as a conversion factor for a variety of different types of problems in making solutions. We have to make sure that we understand what is given and what we're asking for, right? So take a look at the conversion factors that can be obtained from percent composition. The 15% mass by mass of NaCl solution indicates that there's 15 grams of NaCl in 100 grams of solution. So I can use this as a conversion factor between grams of solution and grams of solute. I can do the same thing with my percent by volume. If we have a 6% by volume of methanol solution, that means that there's 6 milliliters of methanol and 100 milliliters of solution. So I can take 6 milliliters of methanol over 100 milliliters of solution and use it as a conversion factor. And the same can be said for mass by volume. So again, reading and interpreting the question, understanding what's being asked of me, and being able to figure that out is super important, including the labels of solute, solvent, and solution as we continue to work through this. So let's look at this next problem that we have here. It says how many grams of NaCl are needed to prepare 40 milliliters of a 0.95% mass by volume saline solution. So as always, we need to see what type of information we're given here, and we're given the volume of the solution and the percent by mass, 0.95%, and we want to know the mass of the solute. Well, again, we can use that percentage as a conversion factor because it contains two different units. So 0.95% mass by volume means that there is 0.95 grams of solute per 100 milliliters of solution. That's what 0.95% tells us. And so we can utilize this as a conversion factor in dimensional analysis. Look how I did this. I start with 40 milliliters of saline, and then I use that 0.95 grams of solute per 100 milliliters of solution as a conversion factor between my volume and my mass. And then I just simply work this out just like a normal dimension analysis problem. We multiply across the top and divide by what's on the bottom, and I end up with 0.38 grams of NaCl. What's nice about this is I can always go back and check my work. I can take 0.38 and divide it by 40 and multiply by 100 and see, do I get 0.95% mass by volume in my solution? So there's lots of ways that we can make sure that we're going through and doing this correctly by checking our work algebraically. Let's look at another practice problem here. This time we want to know how many grams of sucrose must be added to 400 grams of water to make a 3% mass by mass solution of sucrose. So be careful here when we go through and label these things, because it's not asking you how many grams of sucrose must be added to 400 grams of solution. It's saying 400 grams of water. Water is my solvent. So I've got to look at this a little bit differently here. We're given the mass of the solvent, and we're given the percent by mass, which is 3%, and I need to know the mass of the solute. Now, we're going to use this as a conversion factor again, but be extra careful here because we're looking at solvent, not solution. So while I can sit here and say that a 3% by mass solution is 3 grams of sucrose per 100 grams of solution, I can also say it's 3 grams of sucrose per 97 grams of water, because 3 grams of sucrose and 97 grams of water equals 100 grams of solution. So remember, there's two ways we can look at these conversion factors. We can look at it as grams of solute through grams of solution, or grams of solute per grams of solvent. And that's what we're looking at the bottom here. So we can use that as a conversion factor to go between grams of solute and grams of solvent. We solved the problem the exact same way we did before. We're going to take that 400 grams of water, and then we're going to multiply it by the conversion factor where there's 3 grams of sucrose per 97 grams of H2O, resulting in 12.4 grams of sucrose. And again, I can go back and check my work if need be in order to figure that out correctly. So the math here is a little bit different. It's that conversion factor difference I want to make sure that you take a look at. Because we're going between grams of solute and grams of solvent, the conversion factor is not 3 to 100, it's 3 to 97. Again, just a little bit of a difference here when we go through and do these types of calculations. I'll work through another similar style of problem, just like what we did before. It says how many grams of sucrose must be added to 200 grams of water to make a 15% by mass solution of sucrose. So we're going to work this the exact same way. Take a look at the information that's given to you in the problem. We have a mass of solvent of 200 grams. Our percent by mass is 15%, and our unknown is the mass of the solute. So we're going to work this the exact same way. We're going to use the percentage as a conversion factor as it contains 2 different units, but in this time, I want you to think about this, it's not going to be 15 grams of solute for 100 grams of solution. It's 15 grams of solute per 85 grams of solvent or water. Again, that's the difference here. We're solving for solvent, not solution. So again, it takes a little more work to go through and figure out how we're going to go through and plug these in and solve. The algebra is done the exact same way. We start with 200 grams of water, and we're going to multiply it by the conversion factor we just solved previously. 15 grams of sucrose over 85 grams of H2O. And again, notice the units there. Whatever unit's on top of the first step goes on the bottom of the next step, and we continue with that work until we get to our right answer. The resulting solution is 35.3 grams, the resulting solute, rather, is 35.3 grams of lactose sugar. I think it's supposed to say sucrose, but you get the idea here. And again, we can go back and check our work. If we were to take 35.3 grams of lactose divided by 85 plus 35.3, we should get 15%. So again, read the questions very carefully. Make sure that you fully know what's given and what's being asked for, and we can go through and figure these out relatively easily. So let's kind of change gears here and think about a different unit of concentration, and this is the one that I personally am most familiar with. It's the one that chemists are going to be most familiar with as well. It is molarity, and molarity is just equal to the moles of solute over the liters of solution. So you really need to think about your units as you go through and work through this, because I'm not always going to give you moles and I'm not always going to give you liters. You're going to have to do some work in order to go through and figure out how am I going to put this together in order to get my moles and liters? What if instead of liters, you're given milliliters? Well, you're going to have to do a conversion from milliliters to liters. What if I'm given grams of solute? Well, you're going to have to convert grams to moles utilizing the molar mass. So there's lots of different ways that these questions can be asked. So be extra careful Again, look at the information that's given to you in the problem and create a roadmap in order to figure out how to solve for the information you're looking for. So my first question here says, how many grams of NaCl are present in 250 milliliters of a 1.50 molar NaCl solution? So again, we look at what's given. We're given a molarity, which is 1.50, and a volume of 215 milliliters, and I need to know grams. Well, what I do know is that molarity is moles over liters. And so based off of that information, the volume, I'm going to have to get 2 liters. So we do that first, and again, if you need to break it down a little bit more to show the dimensional analysis with that, that's perfectly fine, but 215 milliliters is equivalent, will be 0.215 liters. Well, again, I can't solve for grams in the solution, but I know my molarity, and I know my liters, so I can algebraically solve for moles. So that's exactly what we're going to do here. 1.50 molarity equals moles of solute divided by 0.215 liters, so I can get my moles of NaCl, which is 0.322. Again, this doesn't fully solve the problem because the problem is asking for grams, so we need to go one more step. We need to do some dimensional analysis utilizing our molar conversions that we've talked about in the previous unit to be able to go between moles and grams. So utilizing the molar mass that's found on the periodic table, the molar mass of sodium is 22.99, the molar mass of chlorine is 35.45. We add those up to get 58.44. We'll take 0.322 moles of NaCl, multiply that by 58.44 grams, and give us our gram value of 18.8. So again, questions can be asked a variety of different ways. I'm not always just going to ask you, hey, here's the mole number, here's the liter number, and solve. You're really going to need to think about, how do I actually go through and calculate and solve for the pieces of information we're looking for? Be extra detailed as you go through and work through these types of problems. Now, this one's probably the trickiest out of the bunch. It says, how many milliliters would be needed of a 0.10 molar solution of iron sulfate to supply 55 grams of iron 2 sulfate? So again, we're given a molarity. We need to figure out the volume of this, and we're given the mass of FeSO4. So in order to be able to solve for this type of problem, we need to recognize again that molarity is moles over liters. We're given our molarity, but we're trying to solve for volume in milliliters, so we'll come back to that when we get liters. But we're given grams. Well, remember that we can convert between grams and moles. We do that by finding the molar mass that's found on the periodic table, so 0.55 grams of iron sulfate. We're going to divide that by the molar mass. Again, make sure you follow your units. Whatever unit is on top of the first step goes on the bottom of the next step, and so on. And what we end up with is 0.0036 moles of FeSO4. We can plug this in with our molarity and be able to algebraically solve for liters of solution. So make sure you're careful with this. Make sure you're good with your algebra. 0.10 equals 0.0063 divided by liters of solution. So in order to solve for that, I'm going to take 0.0063 and divide by 0.10. That gives me 0.036 liters of solution. Again, we're close to being done because the last part of the question is asking for milliliters. So we simply take our liters of solution and convert to milliliters. Again, it is a combination of a lot of different things that we've gone through and done previously. So again, make sure you read the questions very carefully. Make sure that you indicate what is given and what you're trying to solve for, and take it just one step at a time as you work through these types of problems. All right. So last couple things that are going to wrap up this unit here. One of these is a dilution. So many times, especially in my chemistry lab that I have at the high school, is that I buy stock chemicals in the highest concentrations possible. You can buy them in weaker concentrations, but it's much easier to go through and make them in the lab because it's cheaper, right? You end up actually just paying for water if you pay for diluted solutions. So it's much easier to just buy the diluted water or the distilled water on your own and go through and make your own solutions. It just saves you time. It saves you, well, it doesn't save you time, but it saves you money, and you go through and make it yourself. And this is one of the most important formulas that I use personally on a day-to-day basis because I'm always making different solutions for different labs that we're working on. And so we have our different solutions here, and we're going to go through and solve for this. So if you take a look, the dilution formula is very simple. It is the initial concentration, C1, multiplied by the initial volume. So it will give you 3 of these 4 variables. You just have to solve for the unknown. It gives you the final concentration and the final volume, and we set them both equal to each other. It's a really nifty little formula that makes things very easy to go through and solve for. I would just make sure that you read the question very carefully so that way you know what your initial concentrations are, your final concentrations. Just make sure you read it very closely. So let's try a practice problem. It says here, what is the molarity of a solution prepared by diluting 35 milliliters of 1.25 molar AgNO3 to 250 milliliters? So I would recommend that you look through this problem very closely. If you see the word of, they go together. So that is the 35 milliliters and the 1.25 molar will go together. That is, they will both be either the ones or the twos in the problem. It does say, what is the molarity of a solution prepared by diluting 35 milliliters of a 0.125 molarity solution to 250 milliliters? So 250 milliliters is the volume we get at the end. So what that tells me is that 35 milliliters and 1.25 molarity are my initial concentration and volume. So that's what we have here. We have an initial concentration of 1.25 molar, a volume of 35 milliliters, and we're diluting it to a volume of 250 milliliters. And I want to know what is the second concentration. So I just simply plug that into the formula that we just looked at. So C1V1 equals C2V2. And I just plug those numbers in, just like we indicated, and we algebraically solve for the new concentration, which is 0.175 molar AgNO3. So it's just a simple matter here of plugging these numbers in and algebraically solving for the one that we do not know. So this is a little bit more of a straightforward problem. It's one of the reasons why we like using the formula as chemists is because it's a fairly easy problem to do. It doesn't require that much work. A simple jot down in your notes and a calculator can make you very easily calculate this. So nothing too much to stress about here. Let's look at this last question here. It says, determine the final volume of a 0.25 molar NaCl solution when using 10 milliliters from a 1.0 molar NaCl solution. So in this particular problem, we're given our initial concentration of 1.0 molar and our initial volume of 10 milliliters. Notice it says determine the final volume of a 0.25 molar. So the final volume is going to be our V2 and our 0.25 molar is going to be our C2. And so again, we just algebraically plug those in, we solve, and that tells us that our final volume is 40 milliliters. Now, I want you to read the second question that's here because it states how much water was added to reach the final volume. We'll take a look at the volume that we start with. We start with 10 milliliters, and then we end up with 40 milliliters. So that tells us that we're going to need to add 30 milliliters of water in order to reach our final volume. It's just the difference between your initial volume and your final volume. So it's a pretty straightforward way to go through and calculate some of this. So hopefully you don't find it too difficult. As always, just make sure that you practice, practice, practice. All right, we've got a couple more things that we want to talk about here before we wrap things up. Let's talk a little bit about electrolytes. And if you've ever seen a Gatorade or Powerade commercial from the late 90s, early 2000s, you know that that was a big deal in sports drinks was electrolytes, electrolytes, electrolytes. And it's a fancy term for a solution that can conduct electricity. Basically, all it means is that it has soluble ionic compounds that are in it. I know it's not quite as exciting as electrolytes, 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 but I think you get the idea here. It's a pretty straightforward concept. The greater number of ions, the better that the solution conducts electricity, so a higher concentration of those ions, a higher molarity of those ions results in an increased concentration, or if it breaks down into more ions, which I'll show you here in just a minute, will conduct electricity more than ones that break down into fewer ions. So how do I determine whether something is an electrolyte or a non-electrolyte? Well, it has to be a soluble ionic compound. Remember that ionic compounds are metals plus nonmetals, and we can determine solubility by looking at the solubility chart. Non-electrolytes are substances that cannot conduct electricity, so these are either going to be dissolved covalent compounds or insoluble ionic compounds, ones that do not dissociate into ions when you put them into solution. So when an ionic compound is dissolved, we know it dissociates into its ions. Let's see what that looks like. So the first one we're going to dissociate is NaCl. And to figure out how many ions dissociate, we need to look at the number of atoms that are present in the original compound. So Na and Cl contains one Na and one Cl. When you put it into water, it will dissociate in a 1-to-1 ratio. So I get one Na ion. Remember that ions carry charges, so look those up on the periodic table. And then chlorine will have a minus charge. CaCl2 is soluble, and it will dissociate into calcium ions and chloride ions. But notice that it is in a 1-to-2 ratio. I have 2 chlorines for every 1 calcium, and that's because there's 2 chlorines in CaCl2. So we just transform that subscript into a coefficient when we go through and write this. And the same rules apply to polyatomic ions. Just make sure you keep the polyatomic ions together as you go through and dissociate it. Keep in mind that if I find that the ionic solid is insoluble based on the solubility chart, then there's no need for me to write a dissociation equation because it will not break apart when you put it into solution. So always check to make sure, first off, it's ionic, and second, that it is soluble before you go through and write out any dissociation equations, because several of them may not have dissociation equations. Also notice our states of matter as well. We start off with solids because before we dissociate it, we assume we're holding a solid. Maybe not the best assumption to make, but you get the idea. And then we put it into water, and once it becomes water, it dissociates into its ions based on the solvation process we talked about previously. And that results in ions being formed that are aqueous in solution. So, should be pretty straightforward to go through and write these. So, let's practice. All right, so we have 3 different ionic compounds here. And I know they're all ionic because they're metal plus nonmetal, so we can all say that these are all ionic compounds, which is nice. Okay, and we want to write out the dissociation equations for the following. So let's just double check and make sure that nitrate there means that this is soluble, so that's good. The Na there makes this soluble. If I actually go and look up phosphates, and I don't know if that's on your solubility chart or not, I'm pretty sure that it is. This is actually an insoluble compound. So we're not going to write out a dissociation equation for that, but we are going to be doing it for the first 2. So we've already got our solids written, so we'll go ahead and write our arrows. And again, think about how many ions it dissociates into. So we have 1 silver that's here. We give it its charge. And our state of matter is aqueous. Nitrates, remember, polyatomic ions, we're going to keep them together. Give it its charge. Gosh. Aqueous. The second one here, Na2SO4, we're going to dissociate into 2 sodiums with a positive charge that are aqueous, and 1 SO4. Again, make sure you check all the charges as you go through and do this to make sure that you write everything out correctly. And those are your dissociation equations. If this did dissociate, hypothetically, you would get 2 aluminums from it and 3 phosphates. But again, it is insoluble, so I'm not too terribly worried about writing out that particular compound. All right? Should be pretty straightforward. Let's see what we've got left over at the very end. It appears we have nothing at the end. I thought I had one more slide, but I guess I don't. So that wraps up our solutions. I know we covered a lot of math this unit, and I covered it kind of quickly. Again, the whole reason why you should be in lecture and use these for like review and not, you know, the main reason you're getting the information from. But regardless, I hope you practice. I hope you enjoyed it, first and foremost. Hope you enjoyed that. And if you did, feel free to like, subscribe, comment, whatever, you know, anything to help me out, I guess. I'm not doing this for the views, man. I just want to share some chemistry love and some chemistry knowledge. So if you'd like it, you can, but not a big deal. What am I getting at? I hope you enjoy your day. Thank you so much for watching. We'll see you very, very soon. I think we got a couple more videos left in this 1030 series, and then we'll be back to doing some AP work. So I will see you very soon, and take care. Bye, everybody.